1, 2, 3, and don't forget to look at the camera, and mark. Hello, and thank you for coming to my poster. My name is Eric Fries, and today I'll be talking about detecting archaeological sites via land surface albedo. For some background, I'm an archaeologist working in Belize on ancient Maya sites. And a lot of those sites are currently under threat because they lie in jungle that is being torn down in order to provide more agricultural land. And as a result, many of those sites are being damaged, in some cases even bulldozed, and it's very difficult to keep up with the pace of deforestation in recording and trying to protect those sites. So, I wanted to see if I could find a way to detect destroyed sites made out of limestone, which is the local stone, by comparing their land surface albedo value to the values of the surrounding terrain. You might be asking, what is albedo? Albedo is a measure of reflectance based on temperature. So for instance, snow has a very high albedo value, water has a moderately high albedo value, desert sand, like we're surrounded by here, has a moderately high albedo value, and things like dirt and trees have a low albedo value. So albedo is often used for climatological studies for things like snowpack cover, expansion of water-covered areas, and things like that. It's not really used in archaeological applications. In the Maya area, most remote sensing is based on variations in elevation. So we use things like LiDAR, which can look at subtle variations in the topography to pick out sites. Spectral evaluation techniques haven't been very successful because the thick jungle cover tends to obscure the kinds of things we want to see with spectral imaging. But here I thought I would try to use a spectral technique, and one that hasn't really had much application in archaeology generally, because of the unique physical characteristics of the sites I'm looking at. They don't have elevation because they've been destroyed, and they are made out of a particular material which is very reflective and often visible on satellite imagery with the naked eye. So, for the method, what I did was I took land surface albedo values by starting with what's called the Landsat Collection 2 Surface Reflectance Dataset. This is a pre-processed set of satellite images provided by the United States Geological Survey. They're pre-processed because the actual measure of land surface reflectance relies on some complicated math that's a little bit out of my range based on raw data. But fortunately, this pre-processed data set exists. And then I processed it further by taking bands 1, 3, 4, 5, and 7 of the data and converting them using a formula from Smith 2010, which takes surface reflectance values from the various bands, weights them proportionally, and spits out an albedo factor. I also had to make sure to select a cloud-free tile for this because, as I mentioned, clouds have high albedo, and that would have potentially confused the data. So out of hundreds of tiles that covered my research area, there were only 7 tiles that were 90% or greater cloud-free. And as you'll see, I still have one cloud in the image that skewed the data a little bit. I then took this albedo layer that I had created, and I clipped it by a shapefile which contains the footprints of all the known white mark sites that I've located within a constrained test area where I knew there was lots of exposed limestone. I then looked at the set of albedo values for all the cells in that area, and I compared them to the cells for the entire research area. And I found that they differed significantly in the range of their values, which indicates that the albedo value range for those test sites can be differentiated from the general environment, and therefore we should be able to pick out other similar cells that have similar albedo values and distinguish that they might also be sites. I made a new raster by selecting all the cells in the study area that fell within that test range of albedo values, and that raster was then compared to the locations of all the known and hypothesized sites within my study area, which is the image that you see in the center. So the test area is that area on one side outlined in black. The process successfully identified all the known site clusters down here in the south, here in the center, and here, and it identified 3 new potential site clusters, Here, here, and here. These are all high albedo values in the orange to white range. This is a cloud, and there's the shadow of that cloud. This is a cloud, and there's the shadow of that cloud. So you can see that clouds do have some impact still, and getting 100% cloud-free image is nearly impossible in this area. Furthermore, you'll see that all the modern roads also have high albedo values. And that's actually good because those roads are made out of the same material, local crushed limestone, and in some cases they're actually made by destroying bulldozed sites and then carting them out to the road and crushing them. And so that material is exactly the same as what we're looking for, which confirms that the albedo value is a property of the material and not due to some effect of human activity in the ancient past that no longer occurs today. So we can successfully pick out crushed limestone concentrations using this methodology. So, in conclusion, we found that indeed, in this particular instance where sites are damaged and exposed, albedo can be used as a proxy for site presence. We identified some new areas that we now have to go check out in person that may have additional destroyed or exposed sites. And furthermore, we can take this technique and apply it to all of Belize and all of the Maya area more generally in places where development threatens archaeological sites in this manner, many of which are remote and difficult to access, but which nonetheless show up on satellite imagery. Thanks so much for coming to my poster.